Great pleasure to be here today. My name is Marc Bellemare, and my main area of research is deep reinforcement learning. And so if you look at that title, Understanding How Value Predictions Shape Deep Representations, that's basically just a really complex way of saying the same thing. By value predictions, I'm going to mean all that we use to make decisions in reinforcement learning. And by deep representations, I really mean how a deep network perceives the world. So what I'd like to do today is tell you a little bit about the kind of research I've been involved in and very excited about in the last few years. And sort of put in perspective the really exciting work we've seen about applying deep reinforcement learning to the game of Go, to the game of to OpenAI 5, to AlphaStar, and sort of ask the question, where are we at and how, what else can we do with this kind of technique? And so just to get started, I want to say I'm actually an incredibly lucky researcher because I've spent most of my research career playing video games. Right? You can't really ask for better than this, right? So what do I mean by this? I really mean I've been training reinforcement learning agents to play video games for me. So what that means is we take a video game and then we take a reinforcement learning algorithm and then have it play this video game by trial and error and learn to play the game as well as a human could. So what you're looking at right now here is a game called, actually, show of hands, who knows what this game is? If I start it? Great. So this is a game called Space Invaders, right? You're at the bottom of the screen, you're trying to prevent the invaders from invading, and as you do so, you're going to receive some points and stay alive. This is actually a game, this particular version is from the Atari 2600 video game console, which is actually now 40 years old, or over 40 years old. And what you're seeing on the screen right now is the reinforcement learning agent playing this game autonomously, okay? And so when we think of doing this with reinforcement learning, there's really three key ingredients: the state, the action, and the reward. In this case, the state is actually what is on the screen, the image that the Atari gives us. So the agent receives this state, and then using that state is going to have to make a choice, an action. In this case, it's a joystick motion. Do I go left? Do I go right? Do I press fire? Do I stay still? And finally, the last part is the reward, and the reward is what tells the agent what they should do. In this case, and for all Atari games, what we've done is we've actually defined the reward to be the change in score. It's sort of a mathematical way to say what you want to do is you want to maximize your score, which is a very natural thing to do if you're playing Atari, right? And so these agents then learn to play the game by maximizing score. And actually, specifically, they want to maximize the sum of the rewards along the way. So the left panel actually shows you what this agent is seeing as it plays the game. This is what we call the value function, and the value function is the predicted sum of future rewards for each possible action. If I go left, how much score do I expect to get? And if I go right, how much score do I expect to get then? Okay? And then what the agent does is actually chooses the best action based on its own predictions. Okay? And so actually, this domain is given to us by something called the arcade learning environment, which I developed during my PhD, and has formed the basis for a lot of the deep reinforcement learning successes. And probably the biggest success is the DQN, or Deep Q Networks architecture. And the DQN architecture was a revolution at the time it was proposed in sort of late 2013, 2014. She led to the publication in the prestigious Nature journal about this algorithm. And so DQN was a revolution because of two things. First of all, it was a whole, what we call an agent architecture. Instead of coming at the problem and saying, I'm just going to apply a simple learning rule or just one equation, there's a whole architecture built around this idea of playing an Atari game. And that involves, for example, some pre-processing, transforming the state into a state that is more amenable to training. Okay? And then some extra mechanisms for training, for example, the replay memory and a target network and a specific learning algorithm. But the second revolution was the use of a deep network to play these Atari games, and specifically the use of a deep network to predict that value function I was showing in a previous slide. Okay. So in a nutshell, what happens here is we feed in the image to that deep network. That's the input of the deep network. And then the output is those 6 values you were seeing before. Okay? And then again, the system looks at the 6 outputs, the 6 values, and chooses the one which is highest to act and choose the action. And of course, because it's a deep network, we can train this by backpropagation. And we do this by using classic reinforcement learning rules, such as Q-learning. Okay, so is this the end of the story? So DQN comes around. Do we now know how to do deep reinforcement learning? And what I'd like to tell you today is that this has just really been the beginning of a new way of thinking about reinforcement learning. Okay? And to explain this to you, I want to go back, and in fact, I want to go back 60 years into the future to some work by a researcher called Oliver Selfridge. And Oliver Selfridge had this idea, which he published in 1959, of an architecture called Pandemonium. Pandemonium was a deep network before deep networks, if you will, or around deep networks. And the key idea of Pandemonium was to say, we're going to have an architecture whose job is to predict everything that it could very much predict. Okay? I'm going to keep this vague for now, but effectively, instead of just having a single prediction, predict the value, let's predict everything we could predict. Okay? And then inside the Pandemonium architecture was this idea of a daemon, and a daemon is very metaphorical here. It just means a hidden unit which makes a prediction at every time step based on local information. Okay? So very much a precursor of the deep networks as we know them today. So Oliver Selfridge proposes this idea, and it has great success, but we can ask the question, so what? Why should we predict all these other things? Okay. Zoom forward by 50 years or so, and Richard Sutton, one of the pioneers of reinforcement learning, says in 2011, publishes a paper about a notion of a horde of daemon, and the paper is called Horde, a Scalable Architecture. So again, an architecture, and this one, inspired by Selfridge's work, Richard Sutton brings back this idea of a horde of predictions, and again makes the case for saying we should have architectures that predict much more than just a value, but really predict everything that they can learn about. And the work's been very successful, but a natural question about this work is, so what? Why should we do this? And what I want to tell you today is that the answer in many ways lies in this interaction between the deep network and the reinforcement learning algorithm. Hence the name, Understanding How Value Predictions Shape Deep Representations. Okay, so I want to go back to Space Invaders and tell you about some of the recent work that I have worked on called distributional reinforcement learning. And in distributional reinforcement learning, we're going to train a reinforcement learning agent as before, except that now instead of just predicting the value, one single scalar per action, we're actually going to predict a whole distribution, okay? So I'll explain this, I'll unpack this just a little bit more. On the right panel here, let me start the video. On the right panel, you have a graph, and there's actually 6 colors. They're sort of on top of each other, but there's 6 colors, one for each action. The x-axis is different levels of return. The return is the sum of the rewards that the agent wants to achieve. And so this is the agent predicting all possible futures, if you will, all possible levels of returns I could receive. And the y-axis is the probability of each of these. Okay? So before you had a static timeline. Now this is showing you in real time what the agent's prediction are, again going through the same deep network that was used in DQN. And so if you ask the question, so what? Why should we be predicting these things? Well, one thing I want to show you with this slide is that if you just look at these predictions, you see it sometimes there's a spike at 0. And that spike is actually really important. That spike is the agent's prediction that if it doesn't do the right move, it's going to lose the game. Okay? So there's really two different futures baked in to the agent's prediction right now. There's one future in which everything goes concern, we keep moving forward, we keep accumulating score, and everything is fine. There's another future where the agent drops the ball, basically, and then loses the game. And that, because it's lost the game, it receives no further reward, and then that's the end of the game. Now, what's very interesting is that if we were to just look at a single value, you can convince yourself that with just one number, you can't represent two different things, right? So only by predicting this whole distribution can we actually get a picture into these alternate futures. Okay. So coming back to the so what, well, it turns out that if you do this, if you actually code this up and train this agent as I was just showing you, and you measure its performance over time, it's significantly better than the DQN method. Okay, so this is a learning curve which we use often to evaluate reinforcement learning agents. On the x-axis, you have the total time that this agent is trained. It's actually evaluated in millions of Atari frames. That's a story for a different time. These agents take a while to train, but effectively, we can train them for the same length of time and ask, how well do they do? So the y-axis is how much score did I receive on average, which is a measure of my performance, right? And what you find out is that about 100 million frames in, the DQN agent, right, from that Nature paper, just stops improving. It's now learned as much as it could, and that's the end of the story for it. Whereas the distributional method, in this case, it's an algorithm called C51, which is the first one we developed. C51 performs significantly better than DQN, and actually is still improving when we stop the trial, right? Huge performance improvement. And in fact, I'm showing this to you for Space Invaders, but that was true across the gamut of all 60 games that we have available to us inside the arcade learning environment. So you can take this idea of distributional reinforcement learning, you can implement it in a very naive way, and that's in fact the C51 algorithm. And of course, once you have the basic idea, you can improve on it. And one of the things we've done over the last few years is take that basic idea and make it significantly better. And in fact, just to give you an example, this is a different method called IQN for implicit quantile networks. And IQN performs even better than the original algorithm, right? So it really looks like we're just at the beginning of something different. Okay. All right, so this is very exciting. We have a method that works really well. And now, of course, as a scientist, before I hand it over to somebody else and say, you should use this in your product or you should use this in your project, I should have some evidence, some arguments for why this works better. And now there's a problem. There's a huge problem. And in fact, I think it was 2 years ago, Yasha came to me and said, so what, right? Why should we care about this? So thanks, Yasha, for that. And the reason for this is because it doesn't make sense. Distributional reinforcement learning, as I've just told you, as I've just shown you, should not work better. At the very least, it shouldn't work better mathematically. So I want to show this to you in comparing the two methods, DQN and distributional RL. Okay? So on one hand, if we look at expected reinforcement learning, average reinforcement learning, where we predict, I should have specified, the value is an average. So we actually predict the average amount of score we're going to receive. And the pathway here is we start with the image, we feed the image through the deep network, output these 6 values, and then choose the maximum value to make our decision. So eventually, if we care about an agent that performs well, what we care about is, does it make the right decisions? And in this case, the decisions are driven by these 6 values. If instead we take the distributional approach, we have the same pathway, but we've added this extra step. And the extra step is to feed the image to the network and then output the distribution. It's a distribution, so what we can do with a distribution is we can take its expectation, we can take its mean, we convert that distribution into its mean, and then we choose the action with the highest mean. So we've just added this extra step, completely without justification. Okay? We're doing this extra work, going through this extra step, and at the end of the day, we discard the distribution. That's just insane. Okay? And in fact, a classic principle in all of science is Occam's principle. Don't make things more complex than they need to be, right? And this was a big pushback against Oliver Selfridge's ideas and against Richard Sutton's horde architecture, because we'd added additional predictions and it didn't seem to matter to the process. Okay? So why does distributional reinforcement learning work better? Why do we see this increase in performance when we look at these learning curves? Well, since the original publication, we've been trying to answer this question. And our scientific spider senses, if you want, tell us that there's something strange going on in here. So to answer this question, what we've done is we've gone back to the basics and looked at some of the environments, some of the domains that we used to work on 10, 15, 30 years ago. Okay, one of them is called the acrobat. It's a very, very simple domain. It's 4-dimensional. And we've known how to solve it with pre-deep network methods for now 25 years or so. It's a very nice test bed to compare what happens if we use distributional reinforcement learning or just the classic approach. Okay? And in this case, we remove the deep network. So we just keep what we call a linear representation. And what you find is that distributional reinforcement learning, that's the green line in the middle, C51, actually performs worse than DQN, the top line. So our intuitions are right, this shouldn't work. Okay? But then if you combine both approaches to a deep network, then the story changes. With the deep network, they both do very well. In this case, they do about the same. It's a very simple domain, but it's very reassuring to say, at least our intuitions aren't wrong. It's just that with the deep network, something is different. And so I've actually gone on with Claire Lyle, who was an undergraduate student at McGill last year, and we've done this detective work of saying, here's all the cases where we think we should not see an improvement or should see something worse, and we've checked it off and said, yes, we're right. Mathematically, there is no reason to use distributional reinforcement learning here. So we have a huge conundrum in our hands, but at least we understand where we're going. The math is right, but once we bring in the deep network, something else changes. Okay? So to try to explain what's going on here, we've gone even more to the basics, to an environment called the grid world. The grid world is very simple. There's actually a finite number of states. There's 100 of them in this case. It's a very famous domain called the 4-room domain. And because it's so simple, what that's allowed us to do is to, if you will, get a picture of what the deep network understands, the representation. And so what I'm showing you on the screen here is what I like to call the fMRI for a deep network's representation. You have 16 hidden units in the last layer of the deep network. And I'm measuring the activation of each of these units across the states. So how strongly does it respond to every state? Red is stronger, blue is weaker. And if you just train on the value prediction, what you find is that this representation is very noisy. There's all these speckles. And it's also not very informative. It's actually copies of the same value. Whereas in contrast, if you predict the distribution, in this setting, what you find is a lot more regularity and a lot more diversity in the representations. So that experiment demonstrates that there's really something fundamentally different going on inside the deep network. And again, if we didn't have a deep network, this wouldn't happen. Okay. So very briefly, I just want to say, once we have these pieces in place, we can actually go back and try to improve the system. And so one thing we're doing right now is we've gone back and realized that the key to all of this is to predict all kinds of things, just like Oliver Selfridge and Richard Sutton proposed time after time. So predicting different value functions specifically, what we call adversarial value functions, leads to a better representation. And this is work we put out on archive just a few months ago. So I'm very excited about this because it's finally we have a handle onto why predicting things makes a difference. We've also gone back to Atari, and in Atari we've confirmed that in fact the deep networks have a different view of things. And so that's also a good confirmation. So just in the interest of time, I think I'm going to wrap up very soon, but just very briefly, it's very clear that we want to take deep reinforcement learning beyond game playing, and it's already being applied to robotics, and I think there's great promise for things like health and translation and all kinds of management tasks. And I think what I'm most excited about is the fact that once we bring in the deep networks into the picture, yes, there's lots of challenges to make things work, but it also opens up a lot of new avenues that were simply not accessible to us before when we were using reinforcement learning without that piece. So on that note, I should thank all of the collaborators on this, and thank you for listening. Thank you.
Thank you so much for a very entertaining talk. Let me give you another so what. So your agent in the simulation that you were talking about takes an action based on the expected sum of future rewards, correct? Well, that's what we do in business. You know, we make investments based on the net present value of expected future cash flows. But there's an issue with business is that, you know, business takes place in chaos, a system that's highly dependent upon initial conditions, and those conditions change every time a business takes an action, but we're not the only ones taking actions. All these other agents with their own reward functions are interacting with the environment. So, can research on games help us to better model the global economy?
Well, that's a tall order, I think, right? I think so. I think what I was presenting today is what we call single-player games. There's only one agent, and the environment is not chaotic. The environment is not out to get you. But there's this much broader body of work on, starting with von Neumann in the 20s, the 30s, on game theory. And this has been applied also in deep learning settings. So for sure, I think, and especially now that we have these very powerful models, we should bring them to bear. I think the challenge here is, where do we get the data, right? And reinforcement learning is exciting for this because it's a way to go act out in the world and get some data.
Awesome. So let's take our first question from the audience. We've got one right here.
I'm wondering the principle that you use to train deep neural network to learn how to play games. Could we do the same? Let's say that we are inputting data from a person doing a task while this person is speaking to someone and input data in the system. Could we do the same principle by looking at a game, now you're looking at a person doing jobs, and listening to this person doing his jobs, so you have input value from voice, from video, and then you train deep neural network doing, and try to read what the person is doing. Is it something that would be possible to be done? And what kind of algorithm would we use to do that?
That's a very good question. So can we actually watch somebody else, a teacher maybe, or an expert, right? This is actually a very active field of research, and in fact, people have demonstrated that one fantastic way to bootstrap, if you will, a learning process is, of course, we don't start from scratch. So AlphaGo was started this way. Here's some expert data playing Go. It's not as general as what you're suggesting, but it's the same flavor, I think, right? Let me show you how to play a decent game of Go, and then from there on, the basics. Now go and get better. For sure.
Next question. Oh, we've got one right here.
Hi, so this is a question from a mathematician. With these methods, I hope you can see.
I don't know where you are.
Yeah, I can't see. Oh, there we are.
Hi.
Perfect.
So with these methods, how much have you explored, or is there some relation to techniques in, let's say, manifold learning?
Very little. So manifold learning techniques were very popular 10 years ago, and I think people got very excited about deep networks and forgot about them. So it seems like a right time to bring them back, especially now that we have more computation available to us. So I'd love to see what we can do with this.
So if you have a question in the back for future reference, stand up, because I can't see you up here too well. All right, right here. Your turn now.
Hi. So you spoke about reinforced learning, and of course you're talking about the probability of having an expectation in the future, and in the past, and this is how you have this recursive prediction. How impactful was Bayesian theory to your approach to the database theory? And was there any type of penalization that you expect to incorporate linear models in the future when those things are applied to more humane applications?
Yeah, so how important is Bayesian theory? That's a very good question. In the context of what I've shown you today, not at all. But it's clear that this is maybe the Achilles' heel of deep networks as they are today. We don't really know how to bake in prior information. And if you're dealing with real systems, you have to compensate the lack of data with some prior. There is an alternate approach, which is if you have a simulator, and that's what people have been doing. The simulator, right, might not be a perfect depiction of the reality, but it's good enough to bootstrap the system again. So maybe that's why these methods haven't been used as much.
All right, well, that's our last question. Thank you so much for a wonderful presentation.